Okay, so now remember what we said earlier. Diagonal matrices are nice. Wouldn't it be nice to have diagonal matrices always? Well, now we have a transformation that changes one matrix to a different matrix. Wouldn't it be nice if we could use one of these transformations to get a diagonal matrix? So that's what we're going to be doing here. We're going to try to do it. I'm not saying that we will succeed. We're going to try doing it. Okay. So first of all, one more piece of terminology, very, very easy. A square matrix A is similar to a matrix B if there is some invertible matrix, if we can find one matrix such that B is the image of A under this transformation. So in other words, if I can change A to B by using similarity according to some invertible matrix. Okay? Now, a matrix now is said to be diagonalizable if it is similar to a diagonal matrix. So what that means is that a matrix is diagonalizable if I can find a matrix P such that P inverse AP is equal to D. Now, this is equivalent, but just moving things left and right by using suitable algebraic steps. It's the same as saying that A can be obtained from a diagonal matrix by multiplying on the right by P inverse and on the left by P. So either one of those two conditions is okay. So a matrix is diagonalizable if it can be changed to a diagonal matrix. Okay? So now if we can do that, because of the fact that similarity transformations maintain a lot of properties, maintain determinants, characteristic polynomial, eigenvalues, and so on, that means that probably if a matrix is diagonalizable, well, it's not quite as nice as having a diagonal matrix, but as close as we can get. Okay? So a diagonalizable matrix is almost as nice as a diagonal one. Now the question is, how do we know if a matrix is diagonalizable, and how can we identify where are we going to find these diagonalizable matrices? Turns out that the answer is not too complicated. In fact, it's fairly easy, and here is what it is. So which matrices are diagonalizable? Well, here's the answer. An n by n matrix A is diagonalizable if and only if, drum roll, brr, boom, it has n linearly independent eigenvectors. So it boils down again to this idea about eigenvectors. Now remember, eigenvalues and eigenvectors, we have defined them in a certain way. We've learned how to find them. Here is one application. If a matrix has n linearly independent eigenvectors, then it is diagonalizable. How do I know that? Well, because in this situation, I can actually find a way of constructing the diagonalization. How do I do that? Here it is. In that case, what we're going to have is that our matrix A is going to be equal to, or is going to be transformed to a matrix D by using an invertible matrix P in this way. Well, first of all, D is the diagonal matrix consisting of the eigenvalues of A. Okay? And secondly, each column of P is one eigenvector of the corresponding eigenvalue, the eigenvalue which is in the same position. Okay? And then if we have an eigenvalue repeated more than once, remember if we have a multiplicity greater than 1 and therefore that eigenvalue has to be repeated in the diagonal matrix, then we're going to have to pick linearly independent eigenvectors for that situation. But remember, under the condition that I've given up above, we have enough independent eigenvectors, so that can be done. Right? So this is the way to do it. So you start from a matrix, you find its eigenvalues, then you find its eigenvectors. If you can identify n linearly independent eigenvectors, what you do is you construct the matrix D, the diagonal matrix consisting of eigenvalues. And again, of course, I have not overemphasized that earlier, but we have to list the eigenvalues, each one of them, as many times as its algebraic multiplicity. And then for each entry, for each column of the diagonal D, we're going to construct one eigenvector corresponding to the eigenvalue which is in that column. And if you have several columns with the same eigenvalue, we'll have to pick linearly independent eigenvectors. Okay? So this is the method to construct it. We're going to see in class lots of, well, not lots, but some examples, and you can do some more of your own for how this works out to be. two easy consequences of the fact that I just showed you, the fact that a matrix has is diagonalizable if and only if it has n independent eigenvectors, is the following. If a matrix has n distinct eigenvalues, then it is diagonalizable. Remember what we said last time in the last class. Different eigenvalues have linearly independent eigenvectors associated with them. So if this matrix has n distinct eigenvalues, so no eigenvalues has multiplicity more than 1, then of course the whole set of eigenvectors, doesn't matter how I pick an eigenvector for each of the eigenvalues, they are going to be linearly independent, therefore it's diagonalizable. So eigenvectors of different eigenvalues are independent, therefore I have enough independent eigenvalues. Another consequence is that for a diagonalizable matrix, the algebraic and geometric multiplicity have to be the same. Why do they have to be the same? Well, let's say, remember, the geometric multiplicity is never greater than the algebraic one. Well, let's assume it is less. Well, what that means is that we're not going to have enough linearly independent eigenvectors. Okay? So if the geometric multiplicity of one eigenvalue is less than its algebraic multiplicity, it means that we're not going to have enough eigenvectors for that eigenvalue to complete the matrix P, and therefore we're stuck. Okay? So if it is diagonalizable, then we know already geometric and algebraic multiplicity have to be the same. So again, this is just a nice way of trying to transform sort of a rebel kind of matrices, convoluted matrices, into possibly something that behaves very nicely, something about which we have lots of nice little information, namely a diagonal matrix. So once again, do some, you want to start doing some practice on your own, and we're going to do lots more in class.